On problem 19, we will continue, or actually begin, exactly the way we did on the other problems. The difference is that this time I've given you a range of values, and I'm asking you to find the global versus local minimums and maximums. So first of all, here is our equation that we need to take the derivative of. So f prime of x, take the 3 times the 1/3 would be 1, and then subtract 1 from the power, so x squared, minus 4. Set this equal to 0 to find our critical points. And either you can factor it into x plus 2, x minus 2 equals 0, but frankly, since there's only one x, it's easier to take the 4 to the other side, or add 4 to both sides. Take the square root, and you have your answer. So our critical points are plus 2 and minus 2, and our endpoints are negative 3 and positive 6. So what we need to do is plug in the values negative 3, negative 2, positive 2, and positive 6 to see which one is our local, which ones are maximums, which ones are minimums, which ones are global, and which ones are local. Now, specifically, I don't want you to use calculus, frankly. You've done all the calculus I need for you to do. Frankly, this is like plotting points back in your algebra class. I just need to know the y-coordinates for all these x values. So you just literally plug them in. So let's go ahead and plug in the negative 3 into our function. And what you'll literally do is just take 1/3 times negative 3 cubed, which would be negative 9, plus 12 would be positive 3. So the coordinates of this point, if you want to think of it this way, maybe it'd be a good idea to graph them. When we're at negative 3, our value on the curve is at positive 3. Okay? Now let's go ahead and plug in our next value, negative 2. And we plug negative 2 into this, we get positive 5 and 1/3. So you'd be up a little bit higher, maybe 5.333 if you prefer the decimal version, when you plug in a negative 2. And now we plug in a positive 2. And we plug in a positive 2. We actually get negative 5.33, or negative 5 and 1/3. So we'd be down here at negative 5.333, squeeze it in. And then finally we need to plug in a 6. And when you plug in a 6, you get a ginormous value comparatively speaking. It's like 48, which is like way up, let's see, positive 3, way up here at 48. Okay? So our curve looks something like this, dips back down, comes back up, right? So obviously, this would be the global maximum. It's the highest that it ever reaches, and the coordinates of that point, I'm sorry, I said 3, this is 6, would be 6, 48. And the local minimum, or the global would be, this is the lowest point that it ever reaches, which is positive 2, negative 5.333, or negative 5 and 1/3 if you prefer. This one would be a local maximum. In this area of the curve, all the way over to about there, all of this, that's the highest point that it ever reaches, and the coordinates at that point are negative 2 and 5.333. And this would be the local minimum because this is the lowest it reaches till about over there. In this area of the curve, that would be the lowest it reaches. And the coordinates at that point, again, are negative 3, 3. And that's really all I wanted you to do on this problem. Just find the first derivative, set it equal to 0, which will tell you what your critical points are, here and here. Then you plug in the endpoints and the critical points into the original equation to find out the y values, and then I just identify your global, local, maximums, and minimums. Okay. Let's go ahead and do our application questions, and we'll call it a day here. So basically here, the population of Colombia was given to you. It's right here. And so you just have to plug that into the derivative equation. So you take off the 100,000, set it to the side, and we're really just taking the derivative of e to the anything. And the derivative of e to the anything is, of course, e to the anything. But once again, this was not just an x, or in this case, not just a t. You have to take it times the derivative of what's inside, times the derivative of 0.02t is, 0.02. So if taking this and simplifying a little bit, we would get 0.02 times 10,000 is 2,000 e to the 0.02t. You put the 0 out there for emphasis if you wish. Then, again, the question read, the population of Colombia was found using this formula, where t is the number of years since 2000. I wanted to know how fast the population was growing in 2010. Since that's 10 years since 2000, we merely plug the number 10 into our equation, and that'd be 2,000 times e to the 0.02 times 10. And the value I got when I did that was 2,442.806. Let's take a look at the next one. It's a very similar problem. The size of a tumor, which has been measured in cc's, is given by this function, where t is the number of weeks since diagnosis. I want to know how fast it's growing at week 3, or I even told you when t equals 3. And I asked you to include your units in your answer. And I probably should have done that up here for you as well. That was the number of people per year that the population is growing. Remember, the first derivative tells you the rate of change up or down. So once again, on this problem, to find the rate of change of growth of the tumor, we take the derivative. Let's set the 7.5 off to the side. And then the derivative of a to the t power is a to the t power, right? Times the natural log of a. Now, since I wanted to know what the value was at year 3, frankly, we just substitute in a 3 for t, plug that straight into my calculator, and I got 0.158. Oops, let me write that a little neater. 0.158, and the units are cc's and weeks. So the tumor, at the third week, at that exact instant in time, is growing at 0.158 cc's per week. Now, the next two are a little more tricky, but they're exactly the type of thing we did in class. We've got this fence, or brick wall, excuse me, and you're going to put a fence up against it. You can use as much brick wall as you want. There's more brick wall than you have fence, frankly. So basically, these 3 sides will be our fence that we'll put 3 sides up against that brick wall. We have 80 feet of fence altogether. So this is x, this is x. So I have a total of 2x feet of fence used up here. Since I had 80 feet total, if I subtract the 2 x's, then what I have left is this amount for this fence. Excuse me. Now, I want to know the largest area that you can have. Well, the area is width times length, or in simplified form, that would be 80x minus 2x squared. We want to find the maximum value, so we take the derivative, which would be 80 minus 4x, and set it equal to 0. This is exactly the same thing we were doing, folks, when we had a curve and you wanted to find the maximum point. Well, this curve, if I were to graph this graph, is the possible areas for different values of x. I want to know this one where it's the maximum. So I just set that because I know the tangent line, the slope will be 0. Since this gives me the slope of the tangent line at any point, I set it equal to 0. Solve for x, and I now know the ideal width. The ideal width is 20 feet. 80 minus 2 times this 20 would be 40. And I asked for the area, so the most area I could have would be width times length, or 800 square feet. Finally, the last one here. Think of this as a chart. I have the number of trees and the number of bushels per tree. Now, I apologize. I know once again my wording here was less than wonderful. And this is the reason I gave you so many extra points on the test. Hopefully, you took advantage of it. Most of your classmates did. And I think the points more than made up for any errors that you made on these problems. And again, you have my apologies. But at any rate, this question is much like the one we worked in class. If you had 50 trees, you got 20 bushels of pear for every tree. Now, for every 5 trees you add, like 55, 60, 65, the number of bushels that you get goes down by 1. So 19, 18, 17, etc. And you want to know the maximum number of bushels that can be produced in your orchard. Well, I made my equation like this. The yield would be the number of trees, which would be starting with 50 plus 50x, where x, or 5x, excuse me, is the number of rows that I go down my chart. Every time I go down one row, that you multiply it by 5 and I have what the number is. Going the other way, I started at 20 and just subtracted 1 for each row. That's my formula for yield. I went ahead and did the FOIL for the equation. I came up with 1,000 for the first. Outside was minus 50x. Inside was plus 100x. Last is minus 5x squared. Simplifying leaves me with 1,000 plus 50x minus 5x squared. Taking the derivative again to find the maximum would leave me with 50 minus 5x, minus 10x. Set that equal to 0. 50 equals 10x. 5 equals x. Now you can either take that 5 and stick it back into the equation, or just figure out what the values would be on the chart. Basically, it would be 75 trees, because you'd come down 5 rows, and 5 bushels less per tree would put you at 15, and 75 trees times 15 bushels each left me with 1,125 bushels of pears. And that's the test.